Here is chapter 22 for nuclear chemistry. These are the suggested chapter problems. If you're struggling, there you go. So just a terminology review. Nuclide is a type of atom. It's specified by its atomic number, mass number, and energy state. So for example, carbon-14 tells me specifically we are talking about carbon-14, mass number 14. Sodium 23, nitrogen 14. So those are specific to that specific isotope. A nucleon is a proton or a neutron. It's part of the nucleus, so it does not include the electron. So nucleons are those particles that are found in the nucleus. An unstable isotope is something that is naturally or can be derived artificially, and it's going to be unstable in the nucleus, so it's going to decay by emitting some type of radiation. Now we've talked about alpha, beta, and gamma radiation, and it's going to do that until it's stable. It's got some sort of stable isotope that it reaches. These are the types of radioactivity we've discussed in chapter 1. So hopefully you'll remember that. Remember, we need to know these particles, what they mean, and how to get them. So alpha radiation, we're going to be giving off an alpha particle. An alpha particle is a helium nucleus. Not spending a lot of time on this because we already went through this in chapter 1. So when uranium-238 decays, it's going to lose 4, a mass number of 4, to become 234. 92 minus 2 gets to 90, which is thorium. So we look this up on the periodic table, and that's going to give you that value. Beta radiation, we're going to be losing an electron. So when we're losing an electron, we're going to say 53 minus -1, giving us 54. It's going to increase the number of protons. So that will actually decrease our neutron to proton ratio. We also have gamma radiation. Gamma radiation accompanies a lot of other types of radiation. However, it is not going to be something that we generally write. This is a decay series for uranium-238. So we said it's going to decay until it hits some type of stable radioisotope. So, or some type of stable isotope of a stable compound, right? So we're going to start with this is a heavy isotope. So uranium-238 has a high mass, and it's going to undergo this whole series of decay until it gets to a stable isotope. So uranium-238 starts as a series and goes through a goes through a series of alpha decay and beta decays until it reaches lead-206. So down here we can see that lead-206 is going to be the stable isotope that forms. So how do we know which it undergoes? Can sometimes it maybe choose to go a different route? Yes, but the first thing it wants to do is get rid of an alpha particle because it's going to want to lower the neutron to proton ratio. It then goes through 2 beta decays, then alpha, 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 alpha. Here it can go through alpha or beta, but eventually it does have to go through that alpha and that beta again. So either way it goes, it has to go through both. It just can do one or the other. We go through alpha and then beta, or beta then alpha. Again, has to go through both. Beta, alpha, or beta, beta, alpha, and back down through beta if we hadn't gone through that second alpha. So we reach the lead-206, which is a stable isotope. You could add all these up. You could say how many alpha and beta particles are produced in one series decay. The number should be the same as it goes through all of this, but then it would take a lot of step-by-step processes. So predicting decay modes, how do we predict which type of decay mode something will undergo? So we know it's going to undergo alpha or beta, but it can also undergo positron, or we can have electron capture. So we have these 4 choices. Which one are they going to do? Well, that depends on the neutron to proton ratio. So this is our band of stability here. So this is where our elements are more stable. So anything outside of this, if it were over here or over here, is not stable enough to be detected. So this band of stability allows us to detect it. Now there's actually an island of stability out here that's near 114 protons and 184 neutrons. But the first thing that you want to do is calculate, so I'll write this in a different color, calculate the neutron, I'll just use the symbol, to proton ratio. In lighter elements, those up to about 30, that could be 1 to 1. So this shows the 1 to 1 neutron to proton ratio. As you go through this, we see that 1 to 1 ratio leaves the band of stability for sure about here, but starts becoming less centralized in that band of stability about 30. So atoms up to a Z equal to 30, the ratio can be about 1 to 1. But when we're up here in this region, it's closer to about 1.5 is where we want to be. And you can find that out by finding the center here. Let's see, the center is about 140 neutrons divided by 90 some protons, something like that. So just find a centralized location, find the number of neutrons and the number of protons and divide them. It'll tell you what we want it to be. But we're going to have to decide, is this ratio too high or is this ratio too low? Does it need to come up to get into the band of stability or does it need to go down to get into the band of stability? And nuclear stability, okay, so what we're talking about right now is affected by the ratio of neutrons to protons. And this is what I was just said on the previous slide, that the most stable nuclei have neutrons that are equal to or greater than the number of protons. So we always want that to be equal to or greater than the number of protons. We don't ever want to have a ratio that's less than 1. Now we do have hydrogen and helium that are exceptions because they're extremely light particles that they're not going to have that issue. The number of protons and neutrons is nearly equal for low atomic elements. This is where I said up to a Z equal to 30. That 1 to 1 ratio is okay. But anything within the band of stability, those are usually stable. But anything that's not in the band of stability, we want to get it to the band of stability. So anything above Z equals 20, the number of neutrons exceeds the number of protons and stable nuclei. But we said realistically, there are, without those two exceptions, hydrogen and helium, everybody has a greater number of neutrons than protons. It's going to be at least a ratio of 1 to 1. But usually nuclides that, even if they have low numbers of protons and neutrons, they're both stable. Even numbers are what we're looking for. So in our lower elements, we see that most of them have some type of stable isotope. But when you look at the number of protons and the number of neutrons, I can do this. I'll just keep the way we're doing it. Number of protons and the number of neutrons. If you have an even combination, that's almost always stable, or it's more stable. If you have an even odd or odd, let me write that somewhere you can actually read it. Odd, even, or odd, odd, it's less likely. So these are going to be less stable, and these are usually unstable. Then there's this set of magic numbers. There are certain numbers of neutrons that are magic and stable. So if it's 2, 8, 20, 26, 28, 50, 82, and 126, these are unusually stable. So if you see one of those, that particular isotope is almost always going to be stable. Any element above Z equals 83 is always radioactive and unstable. So if you see a Z greater than 83, you automatically know that that's going to be the unstable isotope. Now, what do we look at for how we think something will decay? Will it undergo alpha emission, positron emission, or electron capture, or will it undergo beta emission? Well, it depends what that neutron to proton ratio is. If this is you know, again, also what the Z is. So if Z is greater than or, or sorry, less than or equal to 30, then you would want this to be about 1 to 1. We don't really want it to be lower than that. So if it's Z greater than or equal to 30, you're going to want that neutron to proton ratio to be about 1.5-ish, especially towards those heavier elements. So if we need to decrease and bring that ratio down closer to 1.5, beta emission is the only way to do that. If you need to increase and bring that ratio back up, you're going to need to do positron emission, electron capture, or alpha emission. Now, I'm not going to ask you to figure out which one of those two it is. So if you think you could say it's either of these, but you can definitely tell if it's going to be alpha emission or not. We need to get rid of that unstable nucleus. So you might be able to tell the difference between alpha emission versus positron or electron capture, but this one you could say it's either positron emission or electron capture. And if you remember when we talked about this in class, we talked about practice. Try taking a helium nucleus away and see what that does to the ratio. Try doing either of these two and see what that does to the ratio, and that's how you can tell. So practice. One of these nuclides in each of the pairs listed below is radioactive. The other is stable. Which is radioactive and which is stable? Explain. So the first thing you want to do here, first thing is calculate the number of protons and the number of neutrons, and then look at what that means. So what is 208 for polonium? What is 208 minus 84? So we have 84 protons and 124 neutrons. For bismuth, 209 minus 83, we have 83 protons and 126 neutrons. Well, these are both even. This is odd, even. So we might be thinking, well, this is more stable maybe, but let's do the ratio. So the neutron to proton ratio is 124 divided by 84 is 1.476. The neutron to proton ratio here, 126 divided by 83 is 1.51. So this one actually needs to come up a little bit. This one's pretty good. But let's take a look at the main reason here. The first thing that we probably should look at after we figure out the number of neutrons and protons, or maybe even the first thing that you see, this has a Z equal to 83 and this has a Z equal to 84. So you can automatically tell me that polonium is going to be radioactive because its atomic number is greater than 83. So all of that work is important, but it doesn't really matter since it's polonium and it's 84. It has no stable isotopes. Bismuth should be stable because it has a magic number of neutrons, 126, but also its ratio is closer to that of the stable range. I want you to try this, so pause it and try it. So I'm going to go through them right now, so you need to pause it and try it yourself. One of the nuclides in each of the pairs is listed as it's radioactive, the other is stable. Figure out which is radioactive and which is stable, and then explain. So 39 minus 19, this one has 20 neutrons and 19 protons. 40 minus 19, 21 neutrons and 19 protons. So the ratio here is 20 divided by 19, 1.053, and here is 21 divided by 19, 1.105. This is less, a Z is less than 30, so 1-to-1 ratio is okay. So this is still okay for a ratio. So maybe we still don't know yet. Well, we have 20 neutrons, which are even, and 19 protons, which are odd, 21 neutrons, which are odd, and 19 protons, which is odd. So if I had to guess which of these was going to be radioactive, I would say this one because it has an odd to odd combination. And I'll erase the writing there. So also, if we looked, potassium 39 has a magic number of neutrons, which is 20, so it should be stable. So this one should be stable for more reasons than it just had an even odd combination, because even odd can go other way. But since this isotope has odd odd, it's going to be unstable. So this is going to be radioactive. Gallium 71 and gallium 76. 71 minus 31 is 40 neutrons here and 31 protons. 40 divided by 31 is 1.29. 76 minus 31 is 45 neutrons and 31 protons. 45 divided by 31 is 1.45. Now we have a Z here equal to 31. So this isn't exactly that much higher than the Z equal to 30 is okay to have a 1-to-1 ratio. So 1.45 might be a little high for this one to be still in the range. Look here, we have an even, odd, and an odd combination. So if I had to choose, I would choose the one with the odd combination. Let me erase this for you. So this actually lies farther from the center of the band of stability. Like I said, it was 1.45 ratio versus a 1.29. And since we're still very close to Z equals 30, it should probably be closer to 1-to-1. And I don't need to put one dot there, sorry. So this one is more likely to be radioactive to begin with, and then we look that it has an odd number of neutrons and an odd number of protons. So we expect that this is going to be more stable. But also, if you look at the periodic table, the mass of gallium is closer. So gallium is number 31. If you look at number 31, gallium has a mass of 69. So the average atomic mass, which is a combination of all of the stable isotopes, is 69.72. So 71 is much closer to 69.72 than 76. So for many reasons, this gallium 71 is most likely going to be stable, and our gallium 76 is probably radioactive. And this is just you reasoning your way through these, okay? Practice again, pause it, and tell me what type of expected radioactive decay you would expect for these ones. You need to pause it. Okay, 47 minus 20, 27 neutrons divided by 20 protons is 1.35. Calcium is less than 30, Z is less than 30, so this should be closer to 1.1-to-1. So we want this ratio to go down, and the only way to do that is beta decay. So beta emission is going to bring that ratio down. It's going to bring it closer to the more stable isotopes. So you're going to expect it to go through beta decay. All right, now back to the pen. 25 minus 13 is 12 neutrons and 13 protons. Yikes, huh? 12 divided by 13 is 0.923. So we have more protons than we have neutrons. We said we really don't ever want it to be less than 1-to-1 unless it's hydrogen or helium. So we're going to definitely want this to go up. And aluminum is only number 13, so we really want it to go up, but how much do we want it to go up by? So if we were to decay this process by using a helium atom, so 4 and 2, we would get 25 minus 4 is 21, 13 minus 2 is 11, and what's number 11? You look on the periodic table and you find out it's sodium. Would that be more or less stable? So 21 minus 11 is, oh, sorry, something weird in my calculator, but it's 10, right? So now we have 10 neutrons and 11 protons. 10 divided by 11 is 9.09. Well, that went down, right? A lot. A 0.909 ratio went down quite a bit. So what happens instead if we do beta emission? So if we were to do beta emission, we get rid of an electron. Oh wait, sorry, not beta, I'm sorry. Positron. Positron is what I meant to do here. A positive electron, right? What do we get here? We have 25 minus 0 is 25. 13 minus 1 is 12. So now we have 25 minus 12, and we have 13 protons. Oh, excuse me, 13 neutrons. Getting ahead of my, oh shoot, I'll rewrite it. So positron emission, we get 25 and 13 minus 1 is 12. We look and that's going to be magnesium. So we have 25 minus 12 is 13 neutrons and 12 protons. 13 divided by 12 is 1.08. So this is going to have a much bigger effect in the right direction than our alpha. So this would be probably what happens. So this would probably be positron emission or electron capture would work for this one. So, and I'll put the writing up there for you. So aluminum 25 has a mass less than that of the stable isotope. If you were to look at aluminum 25 on the periodic table, the average atomic mass is 26.6, I believe, 26.98, sorry. And it's less than that. So we would expect that this has to come up. So the most stable isotope, actually aluminum 27, is around what they expect it to be. So we would expect positron emission or electron capture. And actually what is seen here is positron emission. So I wouldn't expect you to know the difference between those two. You try, pause it, and you try on your own this time. Don't forget to pause it. All right, 13 minus 7 gives us 6 neutrons and 7 protons. 6 divided by 7 is 0.85. I'm going to guess positron emission or electron capture because we really need that ratio to go up. But let's just see either way what we have here. It's going to be in the way. So, of course, that one's in the way too. I'll put it on the other side. So nitrogen 13, if you look at the periodic table, the more stable masses of nitrogen are 14, and it's right at 14, so you'd expect that to be more stable. So we're going to want this mass to go up. If we want the mass to go up so that we have a larger ratio, then we're going to want positron emission or electron capture. 26 minus 11 is 15 neutrons and 11 protons. 15 divided by 11 is 1.36. This is less than 30, so we want this ratio to be around 1 to 1, so this would be beta emission. So sodium 26, the mass is greater than that which of the stable isotope on the periodic table of sodium 23, so we would expect it to go up. But I, again, am looking more at the ratios that we see, that we want it to be closer to 1.1.